I will begin. We begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this class and this time we have to meet and study your creation, Lord. In your name I pray, Lord Jesus. Amen. All right, so let us remind ourselves. Last time we went over the constant velocity fields, and I tried to go over the kink radiation model, but I neglected to pay attention. So duh. This, of course, is what the electric field looks like for constant velocity, right? The field lines are bunched up and they're kind of smooshed perpendicular to the direction of motion of the constant velocity charge. And so these are the magnitudes increased perpendicular and it's decreased parallel and anti-parallel the velocity, right? So we draw that idea by spacing the field lines out like that, right? The more dense the field lines, the larger the magnitude. That's the way the field line diagrams work. All right, so, and the magnetic fields circle around. All right, so here is the picture I tried to draw last time, and the thing that I failed to appreciate is I had the wrong idea. It says a point charge is at rest at the origin when it's given a kick in the x direction. So it's not that it's just, last time I was thinking it's just moved, boom, and then it just stays there. So I was imagining what it would look like, the field diagram, if you could just magically sort of just take the charge and just sort of relocate it boom, and then just stop there. So I think what I was doing last time would be kind of reasonable for that scenario, but that's not what this is about. This is about, it gives it a kick and then it goes at constant velocity. So after the thing is going at constant velocity, it starts emitting the constant velocity field. So that's what I should have drawn there. It's not the radially symmetric field, it's the constant velocity field. And so there's this, you can't see it very well in the, I don't know, the projector's never, I should have used a different color, oh well. So there's this region where you're going from, yeah, it's totally legal. Definitely not like an illegal Chinese LED laser pointer or anything like that. Certainly not. Just stare at the dot. It won't hurt your eyes. It won't hurt your eyes at all. I wish somebody had a match. We could see if we could light it. But I'm just kidding. This is nothing. I've got one that's. No, I don't know what I'm talking about. So
you shouldn't bring it to class.
Yeah. Actually, I asked a student. She's like, "Do you want me to bring you anything back from China?" And I'm like, "A laser." And she brought me back a laser from China, and it's pretty good.
You can use it to teach electromagnetism.
It uses those the big lithium cells, like you find inside power packs, like the big I forget their numbers. Yeah, those ones. The ones that are they got some heft. I think it's got one or I think it's just got one in there, maybe two. I don't know. But anyway, so basically, what's going on here is that you have the radiation field. You find it here between these two. This corresponds to the place where the charge was accelerated, right? There's this brief acceleration period, and then constant velocity after that. During the acceleration period, the charge radiates. And so this is the radiation field is in that ring that corresponds to a time like speed of light shell that's around where the radiation, where the acceleration happened. So that's basically that. Now, so that's pretty cool. Now, the other thing I wanted to show you guys was the derivation of the curl and curvilinear coordinates, because I did that in Calc 3 today. So this is way, way in the past here, but since I did it, I wanted to show you guys, because you might actually care. If we look at a little infinitesimal patch in the UVW, UVW coordinate systems, so we're looking at W hat coming out at you, all right? So this is all for fixed W, and each one of these is either fixed V or fixed U. And so this, the distance along here would be F to U, where F is the scale factor for U. distance along here would be g times dv, where g is the scale factor for v. And so like the area, infinitesimal area would be like f times g du dv, and we would give it in the w hat direction. And if you calculate the circulation around that little loop, let me zoom out a bit here. You can see that like, so for one, you've got, you know, a dot f du u hat, because that's the displacement there. And so that just picks up the u component of a times the scale factor f du. And likewise, on the top, you're going the opposite direction. That's why you get a minus f du u hat. Now this one is at fixed vw, whereas number 3 is at fixed v plus dw w. So that gives you the work done by the vector field along the top and the bottom legs. And we can do the corresponding calculation on the vertical legs, right? And that's going to pick up, instead of du, it's going to pick up a dv. And so we get this difference, right? But you can rewrite that difference as a derivative, because we're working infinitesimally. Like this difference is the derivative of that times dv, because we're fixing u and w, and we're just taking the difference of v plus dv and v, so that's just the derivative times dv. And likewise down here, we've got gav at u plus du, whereas gav at u, v and w being fixed. And so that difference we can rewrite as a derivative of with respect to u du. And then, so, now Sam, if you, I don't know, this may be too deep a cut, but if you remember my derivation, you too, Shane, of the Stokes form of the divergence theorem, the Stokes form of Green's theorem, I look at the rectangle, we look at the little rectangle, we calculate the circulation around to derive the Stokes theorem. The Stokes version of Green's theorem, the standard version, right? This is exactly that argument. Instead of having horizontal line segments like we did and vertical line segments like I did in my previous Calc 3, and now we just have to have curvilinear sides that correspond to the curvilinear coordinate systems, and we pick up the scale factors because that's how it works. When you have curvilinear coordinates, you don't just have dx or dy, you also have like the scale factor. Anyway, so after the dust settles, you look at it, you got the w component of the curl there from that little argument. And then if you can do it for uvw, you can just as well permute the orders of the coordinates instead and do, you know, vwu or uwuv, just by the symmetry of the uvw here, I can get this and that. So now I've got all three components of the curl, and we can write down the general formula for the curl in terms of uv coordinates as such, which you can repackage in terms of that handy-dandy determinant formula if you do so like, if you prefer that. Now, of course, it doesn't matter for you guys because you guys got a formula sheet, so who cares? But, you know, in case you wanted to derive it, this is the way. And then, so like the scale factors are 1, r, and 1 for cylindrical coordinates, so that gives you, this is the curl for cylindricals that we've used, all right? But the scale factors for sphericals are 1 rho and rho sine phi. So that's why the curl in sphericals is what it is. Okay, my apologies, I'm polluting this class with evil math notation. For these are math sphericals. So don't meditate too deeply on these, for they will corrupt your intuition in this class. Because the theta and the phi, they be switched. Yeah? If you're wondering about how to find the scale factors, what you want to do is just look at the infinitesimal arc length formula, like dx squared plus dy squared plus dz squared. And if you just look at the coefficients of your differentials, that reveals the scale factors. Like scale factor of r is 1, scale factor of theta is r, scale factor of z is 1. Down here, scale factor of rho is 1, scale factor of theta is rho sine phi, scale factor of phi is just rho. Again, my apologies, r is s, and rho is r, and phi is theta, and theta is phi. This is math cylindricals and math sphericals, so everything's all intertwangled. there was a point in my life I didn't understand that there were two different things going on, and I was really confused for a season because, yeah, anyway. So, we have now made it to radiation, right? So let's talk about radiation today. And let me make it bigger so we can see. So when a charge accelerates, they radiate. Usually. Not always, though. So this means that energy is lost from a localized accelerated source. And the question that is, notice I say radiation to infinity. We're only interested in far field radiation in this lecture, which is based on chapter 11 of Griffith's, which is also totally invested in far field radiation. There would also be near field radiation, which would be a far more complicated thing. All right, but this is the radiation that lives very far out. And that basically makes the calculation not too horrible, because it's based on the assumption that R is going to way, way out. And so to calculate the power, we integrate the Poynting vector, right, over a giant sphere. That means we're integrating E cross B over that sphere, all right? And we're interested in essentially all the energy that reaches infinity. Right, because that's the energy that's lost to the system, the far field radiation. So the power radiated at time naught is the limit as R goes to infinity of the power at this time, which would be a previous time, the T naught. Well, I guess that would be there's a substitution there going on, I think. But anyway, that's the energy per unit time which is carried away, never to return. All right? And so let's think about this for static electric or magnetic fields. For static electric or magnetic fields, the Coulomb field is like 1 over r squared with distance, right? The magnetic field is also like 1 over r squared with distance, yeah? So when we look at the Poynting vector from such things, we get a 1 over r to the 4th dependence on distance, right? And so if you integrate something that's got like a 1 over r to the 4th dependence on a sphere of radius r, well, you do get an r squared from the vector area element of the sphere, right? You get I mean, in some sense, it's proportional to this times 4 pi r squared, right? So that, roughly speaking, is like a 1 over r squared. As r goes to infinity, that goes to 0. So the integral of r to the 4th over a sphere, you know, this is, you can think about these details, like dA is r squared times the, surface area element of the sphere. With this, that integrates to 4 pi. So this r squared against the r to the 4th there gives you basically integration of 1 over r squared. And that, as r goes to infinity, is trivial. Which is to say that you're not losing energy in this sense from the static fields. All right. They go on and on forever, but they're not losing energy. All right. They don't contribute to the radiated power, the far field radiated power. Now, so the next thing he looks at is the electric dipole radiation. So electric dipole radiation, he imagines a charge Q naught flowing back and forth between two metal spheres a distance d apart with frequency omega. That's an acceleration of charge. All right. And so that gives us a dipole moment of P naught cosine omega t, z hat, it's also, it's up, down, up, down, up, down. And so P naught here is Q naught d. The voltage that you get from that in terms of the retarded potential business is this. That's your potential. And here the R plus and the R minus are given by this, which is from this diagram down here. Griffith then sets forth 3 approximations. He says we're going to look at the case that the size of the dipole is much, much smaller than the distance we're observing. All right, the field point. And also the distance that the length of the dipole is also much, much smaller than c divided by the frequency of the radiation. All right, another assumption. And then a third assumption is that the field point we're looking at is much, much further away than c divided by the frequency. So these three approximations are used together to simplify the mathematics down to the point that it's kind of manageable. Some power series and binomial series kind of stuff happens, all right? And after some calculation, he shows that, after considerable calculation, he shows that the velocity, the potential is this, all right? And then the vector potential is that. Then he takes the curl and the curl of magnetic vector potential and the gradient of the potential, and out pops. Oh man! Well, that's all I got written actually, so I got it right now. But it was nice while it lasted, right? All right. So we're still in the dipole radiation. Let me show you what he gets us to. What he's going to get us to is this, it's a wave that's propagating outward basically, and I think it's waving in the theta and the phi hat direction if I remember correctly. Here, I'll write it down for us. All right, so I'm not going to do the calculations today. What I'm doing is I am jumping from interesting equation to interesting equation, trying to give you like a summary of the chapter. That's my goal. Because if we just work out the calculations in the chapter, we'll be here till like February. And I really want to get across to you guys the physical content of the chapter, actually. I'm going to endeavor to do that today. We'll see what happens. I'm going to try. So mu naught, p naught, omega squared. Really, it's just applying the things we worked out in chapter 10, honestly. So this is the formula you get for the electric dipole radiation. Subject to those approximations, of course. This is the electric and magnetic fields. I think these are just the radiation fields, technically. Yeah. Here we've got minus mu naught p naught omega squared divided by 4 pi c sine theta over r cosine, or as my professor used to say, cosine of t minus r over c, as Dr. Martin used to say, cosine. He said, call me square root Martin. I only passed the square root of the class. Which is kind of funny because he was really actually pretty easygoing. But anyway, so this is the electric and the magnetic fields from the dipole radiation. You notice that they're in phase, right? Same phase. And, well, the amplitudes are related, but not the same. Notice that this has got this C here, so the magnetic field is, kind of stupidly small because that C there. Anyway, and then, of course, you're interested in what? Power radiated. That's really what we're after. And so that's like the first question to ask is, well, what power is radiated? And so if you calculate the Poynting vector, S, oh man, at RT, I think I got it. Let's see here. Equal to 1 over mu naught E cross B. After some calculation, which we probably could do. This wouldn't be too bad. I'm just being lazy. mu naught over c, p naught omega squared divided by 4 pi times the sine of theta over r. Shouldn't that be squared? Oh, hold on a second here. Hold the phone. Cosine of t minus, well, remember what I was saying about that square? End curly bracket, square. And what do you think the direction of the pointing vector is? R. Very good, r hat, yes. So yes, the radiation points outward, and it's not spherically symmetric, is it? Like there's definitely an angle dependence, and to be clear, like we're talking about a dipole that's situated like this, I mean, it's going back and forth, right? It's going back and forth like that, and so like, let's see here, theta. So, theta equals to 0 is up here, right? Theta equals to pi is down here, right? So, he has a picture of it in the book, but basically what's going on is, and it's squared too, right? Which means it doesn't go, you might, if it wasn't squared, it could be like plus one side. Well, that'd be weird, but anyway, it gives you a donut. So it's like, basically, you end up with this like donut, power donut or something, but it's 0 in the middle. Let's see, power donut.
That is like the whole of the donut.
Yeah.
Through the direction of travel.
Right. Yeah. Well, that not the direction of travel, but the so if I could draw the donut, like the dipole is here. And then the power is the power is radiating in a sphere. That's true. There's this, it's speed of light out from the oscillation, but its magnitude depends on where you are. What's that? Yeah, and the donut. And like, I'm drawing it like that, but the approximations we're making make it essentially a pure dipole, which is oscillating. Like that's part of the game. We're making approximations to make it into the pure dipole field, which is easier to manage. It's really making use of the multipole expansion Griffith admits, yeah.
Would we say that it's 0 if t is less than r over c still?
Well, but no, we're not, it's not an isolated event. This is a dipole which is continually oscillating up and down. It's like making a continuous stream of radiation out. We are analyzing ultimately how much radiation has reached like at a fixed time t or something, but it's not from an instant, it's from a whole like history of oscillation. It's not like the kink model we had before. This is more complicated.
So what I meant by direction of travel, if this was like, I guess that's the dipole moment, like, does the dipole have to be doing that? Could it be doing like that?
Well, the dipole's not moving at all. We're just making charge go up and down in it.
Oh, I see, okay.
Griffith does say that if you made if you did make the charge actually physically move, it would do the same.
Okay, yeah.
So, yes.
I got it now.
What you said. Now if you take the time average over a complete cycle of the pointing vector here, you get this lovely. This equation doesn't even matter. You don't have to write it down if you don't want to. The real one that's of more physical interest is the one I'm about to write after this. So I'm regretting writing this, but here I am this far in, so I'm going to finish it. So that's the average in time over a complete cycle of the pointing magnitude. And then this, he says, after some pesky integration, the time average of the power would, of course, be the integral of this dot dA. And that works out to, actually, okay, the integral's not that bad, but I'm going to skip past it. Mu naught p naught squared omega to the power 4 divided by 12 pi c. So that's the like average power that you get per cycle at radius r from the radiation field. Which is a little bit interesting, right? Because what do you not see there? This is the total power radiated. He said this is total power radiated is found from integrating the average of S over a sphere of radius r.
There's no R.
Yeah, there's no r, right? That's because if the radiation field has a reciprocal dependence on r, one for E, one for B, that gives you an r and an r, which is an r squared. Then that r squared cancels with the r squared in the sphere's area element and just leaves you with a number which doesn't depend on the radius. Just like our usual calculation of like the flux of the electric field. The reciprocal dependence on r cancels with the area element and leaves us just a constant flux for like the static field, right?
Makes sense because the power from one sphere is going to the next sphere.
That's right, yeah. So the power that's going all the way on out has to keep going, right? And going and going, like the Energizer bunny. And there are some things to notice here, though, right? If the frequency is higher, the power does what?
So it's really quick.
It goes up a lot more, doesn't it? Right? Yeah. And so the power dependence is not linear with frequency. It's apparently quartic with frequency. That's kind of crazy. And this actually has pretty significant applications. So here's the main application. Earth. Atmosphere. Sun. That's not horrible stun, yeah. So, all right, so, yeah, don't stare at the sun. Very good, Jared. So, thank you. Appreciate that. As we think about the light rays, the black hole sun, like here, you know, the light rays come in, right? They hit particles in the atmosphere, and they accelerate those particles, which means this happens. And as they accelerate those particles, so basically light hits an atmospheric particle, it absorbs the photon, right? And then that particle wiggles around and accelerates, and then it emits photons as a consequence, right? As it does that, through the process of radiation, that's proportional to the frequency which it emits. And so, oh man, I've lost track.
That's why the sky is blue.
That is why the sky is blue. That's right. So he says the sunlight passing the atmosphere stimulates the atoms to oscillate tiny dipoles. The incident solar radiation covers a broad range of frequencies, which we call, of course, white light. But the energy absorbed and re-radiated through the atmospheric dipoles is stronger at higher frequencies because of the omega to the fourth dependence here. So that's why, here, it gets in here and then it wiggles the little dipole, and then it itself goes in all different directions, right? But it does that more at the higher frequencies than it does at the lower frequencies, which is why we see the blue sky. Comparatively speaking, then when the sun, so I really should have the sun up here for that story, that would be better. So, like this. So here you get the mostly high energy, If I did this right, I would have made the Earth bigger and the atmosphere smaller, because that's really the truth, right? This is still very, very not even close, because you guys have seen the pictures of the Earth, created by that vast conspiracy of people who are trying to, convince you that the Earth is not a flat, but it's a sphere. It's a vast, vast conspiracy. It's really kind of amazing, actually. What's that?
Includes your own eyes.
Includes your own eyes. I mean, everyone knows that the Earth is really a cylinder, but anyway. So if I did this right, as the sunlight gets right at for this point, like right here, there's a point where it has to travel through much more of the atmosphere to hit, like right at sunset. And so at that time period, your light rays that are getting to you through that band of atmosphere are getting much more atmosphere to scatter through. And so that light, which is predominantly scattering at the higher frequencies, you're losing all your blue light because it's radiating every different which way, and all that's left in that sunset time is like the red lights, or the lower frequency part of the white light. Well, I tried, but that's it. Yes, I think so. The Rayleigh scattering, that's what it's called. I think you're right. So he has this very exciting and more accurate picture in the textbook. You can look on page 478. It's very exciting. So next up is the magnetic dipole radiation. All right. So magnetic dipole. Is the next thing he sets up. And I'll just tell you like the start of it and the end of it, all right? So how do you create an oscillating magnetic dipole exactly? Like how's that achieved? You just shake it? Just shake it. I like it. So he says, you look at a current that's given by I naught cosine omega t, and then your dipole moment m of t is given by something like pi b squared I of t z hat, which of course we could write m naught cosine omega t z hat. And so that's your, he says, suppose we have a wire loop of radius b around which we drive an alternating current. That's his setup, all right? So it's like at the origin, the center of the circle is pierced by the z-axis, let's say. And then he assumes various approximations so that we can do the math. Those approximations include that the size of the loop is much, much less than the distance that we're looking at, that the size of the loop is much, much less than c over omega, and 3, that the distance, this is going to be kind of familiar to the last one, the distance is much, much greater than c over omega. These 3 assumptions go into play of giving us the electric field, which results, the far field radiation is simply equal to mu naught m naught omega squared divided by 4 pi c sine theta. So they got the same kind of angular dependence, that sine theta over r terms there again, and then cosine of omega times t minus r over c. This one has got a phi hat, and then the magnetic field gets a theta hat. And it's the same formula, but there's a minus in the front, and there's a c squared downstairs, because it's like the magnitude is similar but not the same. The magnitude of the magnetic field is the magnetic of the electric field divided by c. A familiar story, same as we saw in the last one. So again, it's in phase, right? I think. Yeah, it's in phase. They're mutually perpendicular, transverse to the direction of propagation, which is what? R hat. Yep, R. And man, there's a lot of people out there. Something going on. What's that? Nursing test. Yeah, well, hope nobody dies. Let's see here. S. of RT is equal to, of course, 1 over mu naught E cross B. This is the Poynting vector. And that works out to mu naught over C, curly brackets, m naught omega squared divided by 4 pi c sine theta over r, then cosine of omega times t minus r over c, and curly brackets, square that thing, r hat. The average intensity, right? The average of the Poynting vector is called the intensity. And the intensity here is equal to, parentheses, mu naught m naught squared omega to the 4th divided by 32 pi squared c cubed, close parentheses, sine squared theta divided by r squared r hat. And once more, to find the total power radiated, you got to integrate that thing, right? Well, anyway, he doesn't even show it, but I guess it's probably the same integral as the one that I already skipped over earlier. So mu naught m naught squared omega to the 4th divided by 12 pi c cubed. There you go. That's the average power that the magnetic dipole radiates per cycle. And now he discusses then that, for similar physical dimensions, the electric dipole is totally dominant because you have this division by C in this. And so like he looks at, the ratio of the magnetic power to the electric power. And you get something like omega B over C quantity squared. This is under the assumption that D is equal to pi B, just for the sake of comparing them. So like division by C, right? So, I guess it depends on, if the frequency was sufficiently large, then the, maybe the story flips over, huh? But as long as the C is dominant here, that means the magnetic is like much smaller than the electric, I suppose. Anyway, that's how their magnitudes are related if we wanted to compare the electric dipole radiation versus the magnetic dipole radiation. So next he talks about radiation from an arbitrary source. So there he's just thinking about, rather than just a single dipole or a magnetic or a single electric dipole, what if you've got a collection of charges, right, and they're radiating? And he goes through some calculations, and ultimately he finds that the electric and magnetic fields that are due to like an arbitrary source, arbitrary localized accelerating charge. It gives you the radiation, you get far field E and B as follows. And again, these calculations are essentially akin to the multipole expansion stuff we did earlier. So it's very much in that ballpark of, to understand these more deeply, you need to study the multipole expansion. Like I don't think he even defines P here in this section. At least I didn't see it when I was reading earlier. But anyway, here it is. So the electric field is something like mu naught over, well that's weird, right? 4 pi r. The mu naught there is weirding me out. R hat, watch this, dot the, I don't know what's a good notation for this, but I'm going to do P vector double dot R hat minus P vector double dot. This is the P is the dipole moment, right? the dipole moment of the distribution. Remember we defined dipole moment of a continuous distribution of charge earlier? When we talked about the multipole expansion, we defined the P, which was the dipole moment of the distribution. It was there. Go back. It's what we labeled the second thing in the multipole expansion past the Coulomb term. That thing is what we're talking about here. And its derivatives. Well, apparently second derivatives. Oh, my bad. Well, anyway, this simplifies to, I should have just wrote down I'm trying to write down the finished products here, guys. And so here's the finished product. Mu naught over 4 pi r hat, crossed with r hat, crossed with the acceleration of the dipole moment, p vector double dot. So there is your acceleration field, radiation field for the electric field, and the magnetic field is minus mu naught over 4 pi rc, and it ends up being just r hat across the acceleration of the dipole moment, like that. So at this point, he then specializes to spherical coordinates, and he writes down like what's the electric and magnetic field in spherical coordinates in this context, all right? Assuming that he's assuming that the acceleration of the dipole moment is in the z direction, just for the sake of discussion, all right? So assuming that p double dot is in the z direction, then you have these formulas I'm about to write. In particular, you have E, which is a function of r theta and t, is mu naught, thankfully, the magnitude of the dipole moment, so p double dot of t naught, divided by 4 pi, times the sine theta over r, theta hat. And likewise, almost the same formula for the magnetic field at r theta t. Again, we're talking about the far field, way away from where the charge was accelerating. So p double dot of t naught, 4 pi c, sine theta over r, phi hat. So you put these together, and this gives you the Poynting vector of mu naught over 16 pi squared c. I mean, if I was smarter, I would have just written this down, because what I'm writing right down at the moment is general. Right? This should supersede the previous two examples as special cases, because this is for any distribution of charge, localized, of which the electric and the magnetic are just particular examples. R hat. So this then leads to the power radiated at time naught is just proportional to mu naught over 6 pi c times the second derivative of the dipole moment at time t naught squared. He then shows that if you plug in the electric dipole moment, you reproduce the power formula from earlier by this general derivation. Right? In fact, so, and then, but as his second application, in the case of a point charge, I need to write that, all right, I guess this doesn't matter at this point. Somebody erase this. So for a point charge, if you have a point charge that is, as he says, for a single point charge q, the dipole moment is p of t equal to q d of t, where d is the position of q with respect to the origin, then p double dot, p vector double dot is just what? Q times the acceleration of the charge, right? And what happens to this formula? We get p radiated as what? Mu naught q squared, right? I'm really just plugging it. So like the magnitude here is, right, q times the magnitude of the acceleration, we write a squared, right? No vector, just a squared. And then I've got to divide by 6 pi c. There you go. This has a name. This is the so-called Larmor formula, or Larmor, I should say. This is the power radiated by a point charge is proportional to the square of its acceleration. All right. All right. So trying to pick the part that's there's a discussion in here I wanted to Yar. So later let me just kind of skip ahead a bit here, if I can. So as example 11.3, he has, suppose that the velocity and the acceleration are instantaneously collinear. Find the angular distribution of the radiation. So this is following his discussion on page 490, where he's talking about, I think this is from something called the Leonard formula. And so that formula that he drives is that the power, this is Leonard's generalization of the Larmor formula. And Leonard's generalization of the Larmor formula says that the power is mu naught q squared gamma to the power 6 divided by 6 pi c times the acceleration squared minus the magnitude of the cross product of the velocity and the acceleration divided by c quantity squared. And here gamma, as per usual, is 1 over the square root of 1 minus v squared over c squared. Shout out to chapter 12. So again, this is Leonard's generalization of the Larmor formula. And then, so this is interesting. So he looks at the case that the velocity and the acceleration are instantaneously collinear. So if the velocity is like parallel to the acceleration, then you are able to show that the power is mu naught q squared a squared gamma to the power sixth divided by 6 pi c. And also, when you study it, the power per solid angle, dp of d omega, is mu naught q squared a squared divided by 16 pi squared c sine squared theta divided by 1 minus beta cosine theta to the power 5. That's wild. So here we're letting the z-axis point, the z-axis points along the velocity, like that. A 5. But I guess you could go either way. And so what I'm describing right now, you may have seen somewhere before. I don't know. It's called Bremsstrahlung. Radiation. So like, as he talks about, if you have, so like, he says, although there is still no radiation in precisely the forward direction, most of it's concentrated within an increasingly narrow cone about the forward direction. So like, typical example, something like, you've got an electron, right? And it's got some stupidly large velocity, and down here you've got stuff, all right? And then it hits the stuff, and what happens is there's this super narrow cone of radiation because the acceleration, the electron decelerates in that direction of its velocity, right? So you get this like of radiation from that decelerating electron. This is called Bremsstrahlung.
Did you say that was technically not like exactly in line with
That's what he says, yeah. But this formula, it's large close to theta being 0, but not at theta equal to 0, it's 0. Right? But close to it, you've got something non-zero divided by something that's really tiny. So, yeah. I mean, I guess, I mean, this is technically, that's right. But he says that, no. Okay, I think we have to look at the details, which I'm omitting, right? This would be a great question to ask Professor Budaras towards the end of the optics course, maybe. I don't know. Right? We are just dipping our toes in the pond here, so to speak. Here's some pictures of the radiation pattern, and in this sense, it's like this lobe that goes forward, something like that. Yeah. Now, so there's a discussion in here about why it is. I said at the start this, business about if it accelerates, it radiates, usually, which of course begs the question, what am I talking about? When can you have an accelerating, distribution of charge and yet not have radiation? Any ideas? R cross, I mean, probably. If you ask me about what it has to do with the specific details of the calculation, that's going to be above my pay grade today.
Does rotational acceleration count?
Well, that's a good example. Okay, so yeah, those are the examples. The spinning ball of charge does not radiate, but that's clearly an accelerated charge. Also, if you could somehow take a spherically symmetric ball of charge and just let it kind of like go whoomp, whoomp, like that, just like a cue, and it's just like expanding, contracting like that. All the charge is staying there. Or you're just kind of like, you know what I'm saying? That also does not radiate, and yet it's accelerating. And
Just cancels out.
well, yeah. So he, I think this is on page 486. Let me read this with the. He's got this great sentence about flies mating on a garbage truck, and like some of them fly away, some of them don't. That's his way of explaining like what radiation is. It's like the flies that get away, which is really helpful, I guess. He says, what I've done in this section amounts to a multiple expansion of the retarded potentials. There we go. Carried out to the lowest order in R prime is capable of producing electromagnetic radiation that goes like 1 over R. This turns out to be the electric dipole term. Because charge is conserved, an electric monopole does not radiate. If charge were not conserved, the first term would read blah, and you get a monopole field proportional blah, 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 or whatever. You might think that a charged sphere whose radius oscillates in and out would radiate, but it doesn't. The field outside, according to Gauss's law, is exactly Q over 4 pi epsilon naught R squared, regardless of the fluctuations in size. He says, the acoustical analog, by the way, monopoles do radiate, like the croak of a bullfrog is like a monopole field. He says, if the electric dipole moment should happen to vanish or have a second time derivative of 0, then there's no electric dipole radiation. One must look to the next term, second order in R prime. As it happens, that term can be separated in 2 parts, one of which is related to the magnetic dipole moment of the source, the other to the electric quadrupole moment. The former generalization of the magnetic dipole radiation we already looked at in the previous section. If the magnetic dipole of the electric quadrupole vanishes, oh, blah, blah, I don't care about this. Urgh. Man, I wish I should have circled the section when I read it. But he explains in here somewhere that in those contexts, the reason that you don't get radiation in those cases is because the whole theory of radiation is on about a point charge. And so the critical observation in all this is that the Poynting vector is not linear. The Poynting vector of a distribution is not the sum of the Poynting vectors of the point charges in the distribution. It's quadratic. So you can't add the Poynting vectors of a distribution to get the net Poynting vector, which means that you can't calculate the power radiated by a sum of point charges by simply adding the power radiated by each point charge. It's not like that. It has to be thought of in terms of the entire ensemble. And what's going on, the physical reason that you don't get radiation for the spinning charge or the oscillating monopole is that there's some kind of incredibly complicated destructive interference between the radiation happening. Like the radiation, whatever radiation is happening, it's all canceling out. Like it's not actually leaving. So there's some sort of destructive interference which is stopping the wave from even starting in those situations. That's his explanation. It's somewhere in the chapter. I read it. But I should have circled it. My bad. Anyway, so that is my very sad presentation of radiation. I'm sorry I have not done better for you guys, but I want to move on to relativity. I have more to say about that. Let's move on to that because I know you guys are interested in that, and you would rather I didn't test too deeply on this chapter, right? Yes. So what I'm looking for you guys from this chapter is just being aware of the major formulas like the Larmor formula and just the general story that I've told today. And it would be healthy for you to just read the chapter for your own, edification. So any questions or?
I feel like because the sphere, if it's moving, or not moving in and out,
Yeah.
it's only moving in the R direction.
Yeah.
There's no radiation in the motion, the direction of motion. So there's no radiation going out in the R hat direction, which is all the directions.
But if it's moving out in the R direction over here, it's not moving in that direction. So shouldn't it still be accelerating over here? That's probably it. That's actually probably it. Is the fact that there's whatever radiation you're producing on one side, you're producing the opposite on the other side, and blah, 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 gone. Yeah, I mean, it's got to be something like that, but dang it, there's something I was going to tell you guys.
So does that mean like if you took a different shape, expanded it, it might radiate because it wouldn't exactly.
Oh, I don't know.